What we're going to be talking about today, what are our session objectives? For those of you, thank you so much for all your feedback and letting me know that you can hear me. I'm glad you can, and hopefully you are too. Let me tell you a little bit about our session objectives. Session objectives are a little bit different from learning objectives because they're not going to be demonstrable, or I'm not going to assess your knowledge of this at the end. So it's up to you to kind of get your head around this stuff. But the first objective is that we want to make sure that, that you know how to determine equipment accuracy. So we want to make sure that you know how you can do it yourself. The second thing is we're going to talk a little bit about gauge or fan calibration. We'll talk about the requirements and talk about how at Retrotec, how they actually do that, how they calibrate it, sort of the standards behind it, the codes, and those sort of things. Again, full disclosure, we are expecting to have some experts on calibration, some of our physicists and some of our leaders of sort of industry here and from Retrotec. I am not exactly an expert on subject matter expert on that, but I will entertain your questions and help facilitate you getting answers to that. How to reduce uncertainty in your results. Basically, that's going to be talking a little bit about how to get out there and actually do tests and make sure that you're getting the results that you want. We'll talk more about that. Why does QA and QC equal better accuracy? That has a lot to do with making sure that you have a plan, that you have a process, and that you check it. And we'll talk more about that. And then we're going to be talking a little bit, and hopefully we'll have time. We'll have to get through this. We've got a lot of ground to cover, but we're going to talk about identifying the right process for the right test. So the idea that yes, you have a great process, but does that translate to all of your tests? So with your permission, I will move on. Oh, I do want to mention this. I want to point out this picture right here is actually a manual that you can download from retrotec.com. It is found among the other quick guides, manuals, and other sort of how-tos that we provide you with. Actually, almost a huge sort of encyclopedia of information that's available at retrotec.com in the support page. This is called the Residential Pressure and Air Leakage Testing Manual. We're going to be talking a lot about information that's found in there, and I think that if you don't know about this, please take a look at it online and download it or save it as a PDF. So let's talk a little bit about our first session objective, which is how to determine accuracy. So how to determine accuracy? Well, let's talk a little bit about how you can find out if the equipment that you're using is accurate right now. And we'll try and keep it a little bit more technical, and we'll try and keep it sort of non-specific. So I don't know if people are, or if you're aware of this out here, but it is relatively expensive to actually calibrate. The calibration procedure can be very, very expensive. In fact, it's hundreds of thousands of dollars, or over $100,000 in test equipment that a manufacturer will need to actually calibrate. So if you add in shipping to the consumer, the time away from it, it's really tough to make a monetary case for calibration. In fact, you'll see here that that we actually in our quick guide for, and I believe this is the quick guide for the blower door, I think it's the 1000 series with the DM32, we actually have a whole section in here of how to actually find out if you can calibrate it, or to calibrate, find out if you're calibrated or within a reasonable amount of calibration for yourself. So this comes from the quick guide, and I think we're going to focus on that going forward, if that's okay with everybody. Great. So here's actually, and this is a, I hope you enjoy this. This slide right here basically tells us a little bit about, and very little bit, I don't know, it kind of looks like a Christmas wreath, but it tells you a little bit about what people are doing after they've bought their gauge. How many people are actually calibrating their gauge? So you can see that there's just a tiny amount. It costs about $250 for one range, for one gauge to be calibrated. It's about $100 for each additional gauge. So it's fairly expensive to the consumer. And it shows, you can see that about 5% of our customers, or Retrotec's customers, get them actually done, get their gauges actually calibrated. Only about 1% of customers, that's a really, really tiny amount of customers, actually get their fans calibrated. And it, again, because it's so expensive and it takes time. So what we really suggest to you, and this is in my opinion, well, the best thing to do is to use a hole above a panel and EQLA on a gauge to see if a fan can read correctly. So let's actually kind of walk through that, if that's okay with everybody. Give you an idea of actually how to do that. So with the blower door, there is a nice process, a sort of, and I think a fairly simple process that you can use to see if your fan is calibrated. We call it a field check. We suggest that you do this about once a month, and you can do it on, you can use a full building, you can use a small room. It's up to you, whatever you prefer. I would think that it's probably easier to use a room. Whatever you do, make sure that that room is completely enclosed, or that house is completely enclosed. You want to shut all the outside doors and windows. For those of you who haven't run a blower door before, you want to sort of set it up in the same style that you would if you were actually running a blower door on a house. Or if you're not running it on the whole house, then you want to set it up in the room. You want that room closed off, all the doors closed to the rest of the house. To perform a blower door on a building or a small room, you want to try and record the EQLA. It's probably, so you want to move to EQLA. So if you'll see here, let me see if I can actually do this for you here. There. So you see right here, this is actually a screenshot from the DM32. You cannot actually do this with the DG700, and I'm not entirely sure if the current iteration of the DM2 can do this, but we can talk a little bit about how to do it easily, just as a function of flow. But let's talk about how we can do this very easily at the DM32. We go into the settings, and then we go into results, and we choose EQLA at square inches. Okay? So now what we do is we have our gauge set up. We actually put the blower door into the frame of the door, whatever door we want to use, the one that opens to either the outside or outside of the room. We actually leave the top of it. Now you can see here that there's a wood panel that's been used here, and a square has been cut. Now you don't have to necessarily use a piece of wood. You can use a piece of rigid plastic. You can use any number of things, just as long as you can cut a hole, a square in it that you can measure and that will stay, and as long as that you can seal it tightly into the door frame. All right, so we're going to run, once we've got that set up, we've got our frame below it, we've got this hole, this known hole of a size that we know exactly how big it is, then we can set our blower door in there, and we can run our blower door to 25 pascals, and that's acceptable. So the main thing here about this hole is that you want to know exactly how big it is. Now, for our purposes, we are going to use a hole that is 20 inches by 20 inches. And I'll tell you why, because that's going to be, when we run our EQLA, we want our EQLA to come up, that's the equivalent area in square inches. We want that to be the equivalent leakage area. We want that to show 20 by 20, or 400. And let me explain that again. So we'll run a blower door test with this hole, and then whatever numbers we get, whatever results we get, we write that down. Now, after that, we're going to cover the hole, and then we're going to run a second test, and we're going to compare those numbers. So let me show you this slide. Let's explain it via this slide. So again, I run my first test in this room with this known hole. Now, here I've actually changed this hole to 12 by 12, or 144 square inches. So that's a hole in this panel above the blower door. So I run a test on the blower door, and the results that I get are 168 square inches. Okay, so that's with that hole. So what that basically means is that this is all the leakage to that room. Now I run the blower door again, but this time I cover the opening. So this can be, again, any kind of rigid material. You can just tape over it, however you want to do it. But right here I've covered the opening. And I run the blower door again. Now with this test, I should come up with a difference of the two tests of about 144 square inches. All right? So the test result is the total leakage of the opening and the leakage to the room. That's the first test. The second test, I cover the opening, and the test result now will be something like, say, 24 inches. Here you have this. So if I subtract all the leakage, just the leakage of the room, because I know that the hole's not involved, then I get about 144 square inches of equivalent leakage area, which is this exact hole that I made. Does that make sense to everybody? So again, that's in the quick guide. You can reference that. Sure. Great question. So Tom here asked about, what about just opening a window and closing it? That's no problem, Tom. You can absolutely do that. Just measure that opening in that window, and then open it up to that measuring. It really is a simple mathematical equation. We're just going to find the square inches of that hole, and then we're going to run a test with that hole open. We close that hole, run the test again, and then we subtract our findings from the total leakage from the first test. We subtract the leakage from the second test, and if it should be the same exact size. So yeah, good. That's a good one, Tom. The reason why I usually explain it this way, though, Tom and everybody else, is because I like to draw an analogy to using a calibration plate for the duct tester fan. It's the same sort of principle, but in this one, because of the way that the fan actually operates, we don't have to test a whole completely different room. We can actually use a plate at the end of our that sort of simulates a duct. We can use our flex duct that comes with the duct tester. We can attach a plate to the end of it, and this is a calibration plate that Retrotec sells for under $100. And we know the hole on the end of that. We attach our reference hose, we attach our input tube, which is the blue tube, to the end of it, and do the same thing. We run a test, and we should know, since we know the known hole there, we can compare the known hole at one end to the known hole at the other end, and make sure that they are right. But you can easily do this sort of a DIY method, and I'll tell you how. It's not very hard. You can just sort of add an additional flange with the Velcro or mechanical fastening, and that would be, actually sort of simulating this. You want to make sure it's smooth. You want to make sure that it's rigid and it's a durable material. So, cardboard might be, if you have some really good solid corrugated cardboard, you want to tape around the edge, and you'll see even here that we've actually taped around at the edge. That's because any pressures that we're pushing into it, we don't want it to go around the side. We want it going through the hole. And then we can actually do the same thing. We can use a static pressure probe, stick it in there, and we can run the test. So this works great as a really fast and easy way to check the calibration on your duct tester. Again, this is a test that's detailed in the duct tester quick guide. You'll find it online. We actually have a video. It's also one of the modules that's in our online training. We find that most of our duct testers pass. We do find that when we're using the duct blaster, which is a different, it's a different sort of duct tester. It's made by the Energy Conservatory. That there's about a 25% error on ring 3, and you'll see this right away on that if you test it. So those of you that I mentioned that because some of you said you're using the DG700. I presume that if you're doing any duct testing, you're probably combining that with a duct blaster. Try this test on the duct blaster and try the ring 3 and take a look at what your results are. You also find that this is actually a great learning tool and a way to show skeptical customers or cohorts that your system reads correctly. Let's move on. Everybody's okay with that? So let's move to our next session objective. Let's talk about gauge and fan calibration requirements. So you'll see here, I wanted to, Colin, are you out there? I think I have you. I think you're muted. Let's see. So, Colin, if you're out there, I wanted to ask you a few questions about this particular graph. And basically, let's see if I can make this graph a little bit bigger for you. So, what this graph is this is a test, a graph that shows a typical test that's done on a system. You'll see the 3 different axes, and basically, in general, what we find is that gauges are usually about 0.5% off, or their level of accuracy is usually about 0.5%, 0.5%, which is great. And fans tend to be about 5 to 7% off, or within the calibration range, or I'm sorry, outside of the calibration range. From what I've been told, talking to people that do the calibrations, they say that gauges basically either work or not. They need about a 10% error in a gauge. A 10% error in a gauge will actually cause about a 5% error in a fan. So the gauge is usually the strong link. That means that it's almost a factor of 2 to 1 of how much better it is, or how little it actually affects the actual overall system performance. So this test that we're looking at here shows a pretty accurate test. So Colin, if you're out there, I think you're on the line. I think you might have yourself muted. Can you hear? Looks like you're unmuted. So if we can get our technical difficulties cleared up, we'll come back to this, and Colin can talk to us a little bit more about what this graph shows us and what it's and how it helps. So I'm going to stop actually for a question, Steve. I've got a question from Steve. He says, "What should I do if my duct blaster seems wrong?" Well, that's a really good question, because I kind of wanted to make it. I was hoping that I made it clear, and obviously I didn't do a good job of clarifying the fact that what I've been explaining here, or in the last session objective, or the last section, was how to check to see if you're calibrated. Well, if you check to see if you're calibrated and you're not calibrated, that's when you want to consider sending it in for calibration. So if you check and it's out, you check the calibration, use one of the 2 tests that we discussed, and you did it several times, and you just feel that it's coming up, you're not within calibration every time. Colin, are you with us?
Yeah, I did actually have my mic muted on the wire itself. But do you mind if I kind of back up and make some comments on things you've talked about already?
Oh yeah, absolutely. You want me to go back? Just direct me to one slide.
The list gets too long. Okay. It doesn't need to be a slide. You said that the as far as EQLA was concerned, or you're measuring hole size, both the DM2 and the DG700 will do that. And on the DM2, we call it EQLA for equivalent leakage area, and that's the size of a hole in a flat plate. There's unfortunately another ELA which has the same designations, and we call that the EFLA, and it's the effective leakage area, and it's 0.61 times that leakage area. It's actually the shape of an elliptical orifice, which I'm sure not too many of you have got one of those. The DG700 also has leakage area. They don't really define which ELA it is. I'm pretty sure it's EQLA as well. So you can get square inches on that as well. When we're comparing a window to a hole in a flat plate, a window won't come out to read exactly its hole size because of the detail of the edges and how it allows the air to flow into that hole. So it will measure as being a smaller hole than it actually is. You also made a comment about there being a 25% air on the duct blaster, and it's not the case. Most of them are fine. If they do have a problem, it is on ring 3, and most of them are within the factory tolerance, but we have measured them out as far as 25 and either 30% on that particular range. It seems ring 3 is the one that's problematic, perhaps because the ring itself is so close to the little tube where you pick up the pressure. So that would be the one that you should check, and you can check it quite easily by cutting a hole. An 18 square inch hole is a good size to cut in a flat plate and attach it to your flange in the direction that you normally test. So if you depressurize, I would check the fan in the depressurization direction. If you normally pressurize, then I would check it in the pressurization direction. There can be quite a difference between pressurization and depressurization. So there's a couple of tips there. And typically, if you get it within 5%, you're okay. What you're looking for is some kind of huge, massive error, and don't be surprised if you see one that's really high. That was it for all of what I had so far.
Thank you. I apologize to anybody if I made it seem, especially with with reference to the duct blaster, if I made it seem like it was the entire system. I did mean to say that it was the ring 3, correct? So I apologize for that. So Colin, now that we have you, can you?
It's not all of them by any means.
No,
it's not all of them by any means. It's some, one here or there.
Right, and like you said, it's possible that it's because that particular ring is so close to the input, or the reference, I should say, right? Okay. Well, good. So, Colin, do you want to talk a little bit about this graph? Kind of explain it to the people, tell us what we're looking at, and tell us a little bit about the axes and you know what's plotted out here and how to interpret it.
Sure. Well, fortunately, you won't have to be interpreting any of these graphs. We included that just to show you some of the complexities of calibration. And on this particular range, I think we've probably taken 400 or 500 data points, and to get a really good idea as to exactly how this particular range responds at different pressures and also different back pressures. So, we'll test a device which could be a duct tester or a blower door. We'll test those devices at a whole range of back pressures to see if, let's say, for example, we're testing at 25 pascals or 250 pascals, if it will make a difference. And a great story I had once was a person was testing a commercial duct system, and they were using a duct blaster, which has an axial fan in it. And it's great for testing residential ducts at 25 pascals, but it's not great at testing commercial ducts at high pressure. So he said, yes, I'm reading 850 CFM, and I'm reading 2 or 4 inches of water column. And I said, well, it's totally impossible. It's like you telling me that my old Toyota Tercel can go 280 miles an hour. It just can't. You just can't do it. It's physically impossible. But if you read the manual carefully, as some people do, almost no one does, it says in the duct blaster manual that the back pressure, the pressure that the fan is seeing, must not exceed 100 pascals. And the reason for that is when you're running an axial fan is it doesn't really like pressure all that much. It's really designed for high flow rates. So I took a duct blaster and I lay it on its back so it's blowing into the floor, so its flow is obviously 0. And I turned it up to full speed and I measured the pressure, and sure enough the pressure was 2 inches. And the flow recording was 850 CFM. Now, clearly, there was no flow going through the fan at all, but what's happening is the flow was going around and around and around a circle, just like a big donut, and passing the sensor each time it went by, but the actual flow was 0 through the system. So this is something that can happen if you have too much back pressure and go outside the specifications of the device you're using. So what this graph shows here is a series of different back pressures and so on, and how they are affecting the error. So the kind of brownish dots are errors, and you use the right-hand scale for that. And you can see they go from 0 up to about as high as 3% and down to -3%. And the blue dots are flow, so that's the flow on the left-hand side, which in this case goes up to, I think, 280 CFM, and with a fan pressure at about 1,500 pascals along the bottom. This particular device is one that is used for testing commercial ducts, and it will actually go right up to 30 inches of water column, which is 7,500 pascals. It's a real monster in terms of how much pressure they can create. Very different from the small 25 pascal pressures that we use. And I thought it might be interesting for the people out there to see the extent that we go through to look at our devices and make sure that we understand exactly how they perform. So when you write something in the manual, do this and do that, then you're not going to be surprised. We will put error traps, or we do put error traps in our gauges that prevent you from taking readings that will not be accurate. So when the back pressure goes really high, you'll get a series of dots, and it won't give you a reading. So something is wrong there, and that typically happens when the fan is running very slowly and it's running at a high back pressure. The gauge will actually prevent you from getting a reading. In that case, you have to change ranges, usually to a lower range, so the fan runs faster. One of the rules of thumb is your fan should be, if you can, be running at least half speed. Most of the problems occur when the fan is running at very slow speeds. So that's my little dissertation on that.
Thank you. glad you get the mic fixed. That's the type of information I think this group is looking for. So if everybody's okay, let's move on to the next slide. I want to talk a little bit about, kind of give you an idea of what the Retrotec Calibration Chamber is about, or how it works and how it's built. What you have here is a picture of the nozzle wall. It's designed with, it's an elliptical 1 to 8 inch nozzles designed to, this is an ASTM E1258 standard and AMCA 210 standard. So the calibration test is performed in accordance with these standards, this actual nozzle wall, the chamber itself, is located here in the United States. It's at the Retrotec. Is this in the headquarters? This is in the out in the
in Everson, Washington.
Yeah, in Everson, yeah. But I mean, is it in the offices, or is this sort of out in the factory grounds?
It's in the factory. It's quite long. It's actually in a 20-foot steel container.
Wow.
And we have another one that's 30 feet long. So yeah, they're a little bit big.
Okay. And these are two NIST traceable furnace model 550 pressure calibrators. Serial numbers, I have those. I don't know if I should share them, so I'm going to keep them to myself. But I have those, and they're accurate to what, plus or minus 0.4/100th% of a reading. So the system flow rates are determined using this test, the test fan gauge shown above. So for all these fans, when we talk about, when I mentioned earlier about the cost and about the sort of, I think Colin pointed to the complexity of just the design of the materials used to test. This is exactly what those are. So if everybody's okay with that, Colin, is it okay if I move on to the next part? Any comments?
Absolutely.
Okay.
Absolutely.
Okay.
I could make a small comment on it. Those nozzles that are in that nozzle wall are what the effective leakage area will measure. So when you measure the holes in those nozzles, the area of those holes, that is effective leakage area. So it's kind of typified by an elliptical nozzle, and I'm sure that none of you will have any, so it's a bit technical, but just to give you an indication of what effective leakage area measures versus equivalent leakage area. This particular chamber, we've actually got 4 of them. is designed to automatically test a fan calibration. We do them primarily in Europe, where they insist on yearly and sometimes 2 yearly calibrations. And in all the times we've been in business, which is over 32 years, we've only had 3 companies in North America ask us for calibrations of their fans. We've done little calibration checks, but so it's not a very common thing, but it might start getting common.
Yeah. Excellent. So a little bit more about that calibration, about the calibration process that the chamber is used for. Each of the calibration rates that they test are performed at 3 back pressures. So the calibration is verified at a minimum of 3 flow rates, where one is above or within 10% of the maximum operating flow, and one is below or within 10% of the maximum flow measured for that fan. The calibration at each of these 3 flow rates is performed at 3 back pressures. These back pressures, these are induced pressures, where one calibration point is above or within 10% of the maximum back pressure and measured, and one is below or within 10% of the minimum back pressure measured. So here 10% is sort of the key number. And so that's sort of a little bit in a nutshell the process, the very complicated process that's used and the limitations that are used when calibrating. Is everybody okay with that? Any questions? See, we do have a question here from Dan. He wants to know if I can discuss the effects of temperature on tests. Colin, do you feel like we have enough time right now to discuss that, or should we hold off till the end for that one?
Well, that one's real easy. 16 degrees Fahrenheit will make a difference of around about 1%. And when you run our gauge in software, those temperature corrections come into effect. It's the biggest difference in density. Atmospheric pressure and so on makes very little difference, because how it affects your test fan is the same way as it affects your holes. So yes, the actual flow rate, the volumetric flow rate through the holes changes, but because it affects both the holes in the house and the holes in your fan in the same way, our fans are rigged up so they actually give you the flow that you would get under what we call standard temperature and pressure, which is 68 degrees Fahrenheit and normal barometric pressure and so on. So it's the difference between inside and outside temperatures that have an effect, and it's about 1% difference for about 16 degrees Fahrenheit.
Okay, thank you. Dan, I hope that answers your question. So, and then Colin just talked a little bit about the temperatures, and you'll see that actually comes up on the certificate. So Colin also mentioned earlier that in some Europe, some other areas, they actually ask for calibration certificates, I assume, ostensibly, and this is what one of our calibration certificates looks like. I have redacted some of the personal information, but this is an actual certification. So just so to let you know, digital pressure gauges and test fans are actually calibrated separately. They're done, they're tested separately. The fan calibration must be verified every 4 years, according to our certification here. But that's, I believe, that is according to what the code that applies on there. And here's a little detail.
Can I just jump in there?
Oh yeah, for sure.
The calibration of fans, we say that you can go as long as 5 years. We do recommend that you do a calibration check of your gauges and fans on a regular basis, and if there's a problem, you have them checked. But they are actually calibrated based on the size of the hole in the fan, effectively, and the size of that hole is not going to change very much. What can change is the tubes that connect to that and measure the pressure can either leak or get blocked, and that would be the major problem. So we say that we should do it every 5 years for fans. This 4 years is the U.S. Army call U.S. Army Corps of Engineers protocol, which says 4 years. The state of Vermont might say every year, it might say every 2 years, and that becomes what you must do is according to your local jurisdiction. It's quite common to have instruments calibrated yearly, and I think it's better to do field calibration checks regularly and have them calibrated if there's a problem. But I just want to make it clear that our calibration requirements are quite long, and usually a local calibration requirement of your particular state could be much shorter. Back to you, John.
Thank you. Hey, before you leave, or before you go back to mute, do you want to talk a little bit about the detail here that I've pulled up out of our calibration certificate? Do you feel like that's some important stuff in there, or should we move on?
I think you should move on. Yeah.
Excellent.
There's the odd engineer that might want to play around with that stuff, but there's no reason to know how the gauge does its math. It's shown in our manual if somebody really wants to see it. There's not a mystery about it, but all that math is done automatically. It's kind of like the internet stuff. I just want to press a button and make it go, and I think most people are the same way. So the things you've talked about field calibration are what testers should do on a regular basis, but they don't need to know the math.
Excellent. So that's where we're at. A little summary of what we've done so far is talked about how we can find within a pretty good amount of certainty whether or not our instrumentation, our systems are calibrated, and then a little bit about how we actually calibrate and certify calibration, and how Retrotec does that. So let's talk a little bit about how to reduce uncertainty in your results. I want to talk a little bit about field checking your gauge and your tubes, how to check your fan. We've already talked about checking your fan monthly, and like Colin said, I think the most important thing is, yes, there are many state code, there are many local codes and standards about how often you have to have them calibrated, but if you're not given specific limitations, then it's best just to check them regularly, your gauge weekly, your fan monthly, and decide whether or not they need it. So first thing you want to do, especially now, I know that some of you are using the DG700, many of you are using the DM2, but for those of you who are using the DM32, this is a digital manometer, it's a digital gauge. So one of the great things about having this sort of digital gauge, this Wi-Fi gauge, or even when it's not a Wi-Fi gauge, is that we can actually connect it to the internet and we can do updates. So this guy, it has a firmware in it, just like your smartphone, and it can update itself just like your smartphone. So we want to make sure that always want to make sure that you're using our configurator on your PC, and that you are making sure that you're up to date on your firmware. So the current version right now is 22.2, and that's build 49. I'm going to move on unless anybody has any questions about that. Let's talk about how you actually would field test, the sort of weekly field test of your gauge. If you don't have to just do it every week, if you're testing a lot, maybe 3 or 4 times a day. I know there's plenty of people in the weatherization field who are doing, 6, 7 blorters a day, 5 days a week. They might want to test this a little bit more often. So this field check is for the gauge, it's for the tubing, and it'll help you get really quickly an idea of whether or not you're correctly calibrated, or if there's any problems with your tubing. It's a very simple process. So what you want to do is you want to connect a red tube between the red and the yellow ports, and you want to connect your green tube or your yellow tube, depending on if you're running a duct tester or if you're running a blorter. But you want to use your tubes and connect them to various ports on the gauge, and I have a slide right here that kind of illustrates that. So imagine that these tubes that are connected here at the top of the screen that's one tube. So these are 2 separate ends of the same tube. So essentially what you're seeing here is that we're going to take each tube, and then we're going to connect it to a variety of the ports on the gauge, and actually pressing those tubes onto the ports actually creates a pressure in there, and we'll get a reading. So that reading, that result that comes from the tube between the channel A and the channel B should be within about 2%, and they shouldn't drop rapidly. So you'll see here, this is almost spot on. What this basically tells us is that this end, now again, this tube that you see here this is one end and this is the other end. They're connected to both sides, to the two separate sides of the two separate channels of the gauge, and they're within 2%. If they weren't within 2%, we might have a problem with one of these channels, we might have a problem with both channels, or we might simply have a problem with the tubing. So if you perform this test and you're not within about 2% of the reading, and it doesn't make any difference if it's -50 or -200, that's another sort of technical physics sort of a discussion about how those can be different. But the point is, as long as this reading on channel A, which is this one, and channel B, which is this one, are within about 2% or don't drop rapidly, then you're okay. But if you're not, then the first thing I would do is check your tubes, because a hole in the tube or a cracked end could actually cause that problem first. Pretty simple, pretty quick. Is it okay if we move on to the next slide? Any questions?
Yeah, if you do have a problem there, the first thing you would do is, if you've got the green going to the negative of channel A to the positive channel B, so that's why one channel is reading negative, the other is reading positive. Oh. You're actually checking your negative side of one gauge to the positive side of the other. But if you do have a difference, and one of them is out by quite a bit, then the first thing you do is just try another tube. So here we're going green to green, just try a yellow tube and go yellow to yellow, and then you're checking the tube and the gauge at the same time. And it could be either one that's at fault. So if the yellow tube gives good results, then it's obviously something wrong with the green tube.
Right, sort of deductive reasoning. Thank you for pointing that out. So the next thing we could do is pretty simple. Just take lots of reading. This is actually an excerpt from the manual that we discussed earlier. I believe this is page 10 or 11, and it just simply states that test results uncertainties vary by changing the number of baseline points, the baseline time, and time averaging for induced pressures. So what we're seeing here in this table is the same a test run multiple times. And we're seeing how on this side over here, how the percentage of uncertainty actually goes down starts at 22% and ends up with about 5.9%. Colin, anything do you think that we should to point out about this? Any kind of technical details that you think that are important to point out?
Well, what this points out is the effect of taking readings for a longer duration. This is primarily meant for, say, automated tests, and in this particular case, these high percentage errors would be under windy conditions, where the very best that you can do from a theoretical perspective is to get down to the fan accuracy, which is 5%. Now, there may be no inaccuracy at all, So on the right-hand side, you'll see on the very bottom row, the fan error is 5% and the uncertainty is 5.9. So we've got within 0.9% of the fan error. So if the fan had no error at all, we'd be within 0.9% of the actual result. But you'll notice if you take only one baseline point for only 5 seconds, and that the baseline in the 1, 2, 3, in the 5th column, it says the baseline is varying by 1.5 pascals, then our uncertainty can be very high. So by baseline variation, what we mean is when you plug in your gauge and you throw a tube outside and you look at it, the gauge will be varying, let's say, from 0 to 1.5 pascals up and down. That's what we call baseline variation. And those are the conditions under which you have the biggest problem in getting a stable reading is if the wind is blowing on your tubes and causing it to vary. And this shows you how to get around that by taking a baseline over a much longer period of time. And again, this is in automated software. Back to you.
Thank you. Any questions about that? It looks like looking at my dashboard, everybody's paying attention. We've still got everybody here, so thanks, Helen. I think that really clearly is, very informative. So let's go through our fourth session objective. According to my clock, we've got about 2 minutes to finish up here, and then after that, Joe and I and we always like to stay on a little bit later and answer any questions. So if that's okay with you, I'm going to move on. So we talked about QA and QC and how that equals better accuracy, but so up to this point we have really concentrated on the equipment. So let's talk a little bit and sort of quickly about the people, about the process. And that's what quality assurance and quality control is. And of course, I didn't mention this, but training's in the middle, because you can't have these two, have to be connected by this. The point is that quality assurance, what that is, that's a plan. That's a design. That's where you say, we're going to test this way. And when I talk about test, I'm not talking about the calibration test. I'm talking about the actual performance of the equipment that you're testing, whether it be commercial, residential, duct, or shell. Or sorry, or any number of things you might be testing. But the idea is that this is our quality assurance plan, this is who does it, this is how they do it, these are the steps of service. Then of course we train our people or train ourselves to make sure that we're trained on whether it be a standard that we're living to, or an outside code, or whether this be an actual standard operating procedure for our company. We're trained on it. And then we do quality control. Quality control is just basically a way of going back and seeing if we did what we said we were going to do. So if everybody's okay with that, I'm going to move on to, I just wanted to make sure that we all had a firm base so that we all could talk about this, but I don't see any questions, so I'm going to move on. So one of the first things to do is, and this is what we talked about, is standardizing a reference. Any idea out there is this reference right here? So this is a blower door on a residential home. This is a reference hose that is about 3 to 4 feet directly in front, pointed back at the fan, and this house is being depressurized. So we're looking from outside the house. Does anybody think if this is okay to have this set up like this? Thanks, Terry. So I'm getting a lot of activity out there, and generally people are saying no, and all of you are absolutely correct. This is not okay. In spite of the fact that we can, use an automated test and do it the same way that that Colin just explained so effectively, we still are going to get skewed results if we don't have the simple reference hose set up. Now, it's been my personal experience. I've seen many times. In my background as a weatherization person, I've probably seen over 1,000 times where we've done a standard blower test, ASTM residential standard test, where we've had a assessor or a energy assessor go out to the house, run a blower door test, had a contractor come out afterwards, run a blower door test, same place, same configuration. And then a third time, we've had a quality control inspector come out there and get wildly varying results. And we've started to realize, and you would get people talking about, we constantly heard, oh, their fan's not calibrated. When was the last time they sent it in for calibration? When was the last time that they checked it? We would check these fans and find out it wasn't the fan. What we started to find out was that it had a lot to do with 3 things. One, where their reference hose was. Now keep in mind that a reference hose, that of course when we're using any kind of gauge, it's a manometer, and a manometer is always a differential pressure gauge. So that's the difference between 2 points. It's not absolute pressure, it's the difference between 2 points. So if your reference that your input is referenced to, the difference between those 2 points, if that's off, then your findings are going to be off. And if one guy has the hose here and the other guy has the hose out exposed to the wind, and if we're just doing, again, a specific single point residential test, we can find all kinds of problems with this. So this is a best practice that we started to do, where we actually built this sort of just reuse this plastic. I think this was actually dishwashing detergent or something, where we cut a hole in it, poked a tube in it, put that tube inside of a tennis ball that had been perforated, and then stuck it inside of some rocks and put the top on it. And now so what we did there is we standardized our reference hose. So now we knew that the house was set up in the same way, and that was the other problem. Now, if you're doing retrofit, you have to make sure that everybody testing the house understands where the thermal boundary is. It can be one shut door can actually make a completely different test, pre-post test, or give you an inaccurate result. So here's the idea. This thing right here, now this guy is taking that reference hose, taking out from in front of the fan, moving it over here. He's going to actually stick it into this little thing here, and then put it over here where it's hidden, away from that corner of that building where turbulence and wind can actually move around. So, we've got a question here from Joe Menosh. He says, same issue if interior tubing is near the front of the fan. So, good point, Joe. That's exactly right. So, again, this fan, as we see it right here, this fan is actually moving air from the inside of the house and blowing it out to the outdoors. Now, I'm sorry, the opposite. It's moving air from the outside the house, and no, I'm sorry, I got confused. So it's moving air past through this known hole and then out. So sorry about that. Point is that if your manometer is laying on the ground, or your gauge, whichever kind of gauge you're using, is on the ground, or if you have a tube that sticks out of your input and it's laying here in front of this fan, it can actually cause air to move across that tap, that port, or that tube, and that can really skew your results. Thanks a lot, Joe. So last thing I just want to mention is just make sure that when this frame is installed that it fits snugly. That can actually cause problems, and especially in the tighter houses, your results can also vary greatly. So same sort of idea, same sort of concept, but applied to duct testing. When we're testing a duct, we are going to reference the inside of the home, or technically the outdoors, right? Pressures from the outdoors, because we're going to keep the outdoor a door to the outside or a window to the outside open. But the input is going to be, the input tube is going to be somewhere along that duct, usually right inside the nearest supply register. So what happens is you want to make sure that you're not using a standard pitot tube. That you want to be using the better tube you use is actually a static pressure probe. And the difference again is the fact that this tube, if it's stuck inside of a duct, then you have actual air moving this way or moving across it. We can cause all kinds of turbulence, or actually wind pressures moving inside it that are not giving us accurate readings. This one's a little bit better, but we can still get air moving in front. But now here with the actual static pressure tube, we do not have to worry about which way this thing is pointing, and air actually blowing directly into the tube and giving us skewed pressure. Right, and thank you, Joe. Also, Joe just wanted to mention that that we also need to make sure that this one is actually taped in there. Oftentimes, it's a really good idea to make sure that it's really securely, that this piece right here is securely placed or taped in, so that also vibrations along that tubing doesn't cause bad readings or inaccurate readings. So I want to go through, if it's okay with everybody. I know that we are running about 5 minutes behind. If it's okay with everybody, I want to finish this part right here, and I want to talk specifically about a couple of things, or an issue that Colin Rose that brought up about some of the readings, some of the catch. I think Colin, what was the proper terminology? The catches that are in the gauge that show us that we're actually doing something wrong. I want to talk a little bit about troubleshooting your process. So here we're talking about, this is what Colin mentioned earlier, that hey, we're running this test, and this one is a duct test. And I'm reaching the pressure that I want to be at in the duct, which is 25 pascals, but I'm not getting any flow. And what's causing that? So we're reading this sort of a dash. It's not saying 0 because that's not a pressure. it's not giving us any reading. So what's happened here is that the gauge has it's detected an error. So it's telling us this is the error. So what we need to do is add a flow range or a flow plug, or a range plug, I'm sorry, depending on if you're using a Model 200 or a Model 300, for a more restrictive hole size. And remember to add to make sure that you adjust your gauge, and that's regardless of what gauge you're using. You definitely want to make sure that your gauge is configured correctly, so that it matches the ring, plug, or whatever you're using. That's the setup of the current configuration of your fan. Make sense, everybody? So let's move on to another example. So what happens if we just cannot reach the pressure? So we're getting a flow, so we're not having a problem with the flow, but we can't reach pressure. Well, there's a couple things that we can do. We can actually remove a ring or a plug, and then, of course, again, change the setting. Or we can look for possible reasons that we can't get the pressure. Here in a house, it might be that there's an open door to the outside or an open window. With ductwork, the duct or grill mask may have blown off. Especially, this is especially a common pitfall if you're doing a pressurization test, where you might blow the grill mask off at one of the grills. And then the last thing we can do, so we're checking that, and then the third thing we can do is just try and tap at pressure. And now this is a function of the DM32, where we can actually use this at pressure, and that will give us it will calculate what the pressure would be if we were exactly at 25. And sometimes this is really helpful for people who if they're getting if the pressure is moving around a little bit, maybe from 23 to 26, whatever. You tap on this, and again, this is a touch screen. It's a function of that touch screen that's on the DM32, and it will give you sort of extrapolate what that pressure would be. So let's see, at this point, if everybody's okay with it, I'd like to move over to questions. Officially, I'm going to turn the recording off,